It seemed that the crab was thinly and evenly distributed, with gas moving in all directions, clearly signaling expansion of matter from a central explosion. Determining the observed rate of expansion and the size of the nebula gave an age to this object, an estimate of 800 to 900 years. It was left to Hubble to point out that the coincidence of position and age of this nebula definitely connected the guest star of 1054 AD with the Crab Nebula. The nebula was, in fact, a supernova remnant. It seemed that an energetic central engine might have been left behind by the explosion, something that was responsible for the presence of highly energetic charged particles and high magnetic field in the Crab Nebula. These questions were to be answered later. Meanwhile, a very significant step forward in our general understanding of the evolution of stars took place in the early decades of this century. The source of energy in the central regions of any star, fusion of lighter elements like hydrogen or helium into heavier elements, which stops a star from collapsing under the pull of its own gravity, was well understood by this time. However, the aspects of stellar evolution, when these central energy sources were exhausted, was just being understood. Stars like the Sun would end their lives peacefully and become dense white dwarf stars when the fuel of hydrogen and helium gets exhausted. More massive stars would go through successive stages of burning heavier and heavier fuel all the way, till a dense iron core forms in the central regions of the star. This being stable against nuclear fusion to higher atomic number elements, a catastrophic end awaits the star at this juncture. The stellar explosion takes place at this time when the interior nuclear fuel of a star is exhausted, and the star is unable to ward off the inward pull of its own gravity. The core of the star now collapses to nuclear densities, becoming a neutron star, essentially a dense ball of neutrons packed together in such a manner as to fill all available quantum levels of energy. The core would have to be larger than 1.4 times the mass of the Sun in order that the collapsed object comes to rest as a neutron star. This is the celebrated Chandrasekhar's limit. For lower core masses, the star is able to come to terms with a relentless gravity that tends to compress it by the quantum mechanical behavior of electrons in a white dwarf. In neutron stars, it is the quantum mechanical behavior of neutrons that resists further gravitational collapse of the object. At higher masses, even this would not be sufficient to hold off gravity, and the star would collapse to the ultimate exotic object that occupies zero volume, the black hole.